All right, okay, great. So back again. Welcome back to Channel 9. Channel 9, there it is. I got my man this time. Got my man to help me out. Okay, got Charles here as well. Good to have you here. Okay, welcome back for the third part of the F# introductory tutorial that Charles invited me to do here. So this is the third and final part of the introductory tutorial. We're going to be doing an advanced tutorial or advanced topics tutorial in probably next time I'm here in Seattle, in Redmond, in April or so, and I look forward to that. And but today we're going to be dealing with the topics we didn't get to in the last tutorial, because you always plan to get through a lot, and we didn't get to everything. First, the recap. There's the summary slide that we've been using in the first two parts. F#, general purpose, efficient, succinct, functional first, .NET programming language. Simple, script-like initial experience, but strongly typed and .NET friendly. Highly interoperable and can build vanilla .NET components. Now it's got some nice features for objects, async, agents, parallel, and units of measure, and the language side. Plus, it's got everything you get from .NET when you go and use it as a .NET programming language, and it's got and it's also can be used. It's kind of platform neutral. You can use it with Mono and so on. You can generate code that'll run well under Mono and the other implementations of the common language, the CLI, common language specification. Right, common language infrastructure. So let's take a look at the tutorial topics. Yesterday, the first ones, we got through some fundamentals about what F# is for, why we're doing F#. Then we looked at some functional data and some sequence data in the last tutorial. In this one, we're going to look in a bit more depth at pattern matching, some basic object-oriented programming, and some basic imperative programming. These are really the core topics that you need just to be able to just do general purpose programming with F#, on the assumption that you're also pretty happy to go away and learn the .NET libraries you need to use, learn the F# libraries you can use as well. Right, so at the end of the last tutorial, we looked at this problem about implementing blackjack, okay. Keeping it simple that aces are always worth 11. And it's a very simple problem that we had to model some data. We had to model a hand type, and we had to judge some hands. Okay, so let's take a look at the solution to this problem. So here we have a script which is here. I've got to say, all of the code we're using in this tutorial is available in the F# tutorial zip that is available on my blog. Just look for Don Syme F# tutorial, or just go looking at my blog, you'll be able to find it there. It was a tutorial originally given at the JAOO conference in Aarhus in 2009, in September 2009, and we've been hosting the tutorial code on that particular page. There are other F# tutorials available on the web too, so please go and use those if you like. There's a lot more code in the tutorial zip as well, much more than we're getting to look at today. Some great asynchronous programming examples, some great some small applications that are interesting. There's a famous DirectX demo if you want to see one with a parallel agent in the background for the simulation engine. And but first we'll take a look at this particular file, this exercise solution file from that code. Right, so we've got a suit. Hearts, diamonds, clubs, or spades, a simple union type, we'll define that. And we have a rank of the suit, modeling the ace, king, queen, jack, or a value here. And we'll define that. Now we have modeling a data type of cards. A card is a rank and a suit put together. And then we have the full deck of cards here. Generate the full deck of cards. We saw this last time. And double check that we might show the full deck of cards up on the right here. Here are all the hearts, the diamonds, and the clubs, and so on. Right, and we better check that the full deck, we were pretty keen to check that its length is 52, for example. Okay, there it is. Great. So, when we looked in the last tutorial, we looked at a function card value to work out the value of a card, which takes a card here and returns an integer. And we can define that function here. And we can, for instance, check out the value of the ace of hearts here. We can, for instance, show the value of the ace of hearts here is 11 up here. And you may immediately write, say, a test case to check that to check that is 11. Okay, we can also take the full deck and we can map across the card value function to say get the card values for each of the cards in our deck. You see the 10s here, plus an 11 for the ace, and so on around for all the cards in the deck. Okay, great. Card value and show. Right, so the aim of the exercise is to work out whether a hand in blackjack is busted, a hand value less than 21, or blackjack on 21. So to judge, it's pretty straightforward. Let's take our cards here. We have a list of cards coming in, and we have to work out the hand total, which means taking the cards, mapping across the value of each card, and summing those up. Okay, so now once we've got a hand total here, if the hand total is some n, when n is greater than 21, then we're busted. Okay, and if the hand value is 21, then we're blackjack. If the hand value is n, then it's a hand worth n. Okay, so here's our exercise solution. And there's a few other ways you might have written this. People versed in F# might know that you can actually just do sum by card value here. Makes the code a little bit shorter. It's also perfectly okay if your intuition was to write, say, an if then else. If hand total is greater than 21, then busted. Else if hand total equals 21, then blackjack. Else hand of the hand total, like this. Okay, we'll get rid of that code, and we have the same function. It's really okay to write that function either using pattern matching on the hand total or using the case by case with the if then else. Right, so we've got our judge hand, and now we can judge a hand which is just the ace of diamonds. We can judge a hand which is 2 aces, ace of spades, and we see we're busted because we're counting aces as 11. In the tutorial code on in the zip I mentioned before, you can find the rest of the code shows what if a hand can have value 1 or 11, an ace can have value 1 or 11, as in blackjack, and you have then you're working out a possible hand totals, generating a list of possible hand totals, and then you're estimating those hand totals, and you judge their value, and you sort them, and you take the first one, the best value that's possible. Okay, but you can run that code from the exercise solution. We won't go across that further today. Right, so let's take a bit more of a look at pattern matching. We've already seen some basic patterns. Here's just some more uses of pattern matching. Let's do a truth table where we test an AND. X and Y, match X and Y. You can match on Boolean values here. If it's true, 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 false, you get false. So on, it's just an AND table, a truth table. Okay, so it's a simple truth table. Just to mention, you could have written that more succinctly by getting rid of all the false cases and just having an underscore for the false case, which is like a fall through. The underscore pattern will match anything. Now that's quite nice. You have to be a little bit careful using underscores because you won't get any warnings if you're missing cases. Okay, so here's showing a potential missing case here. You're missing false true, and it will tell you there's a missing case. The error message is a little longer than this, but it'll tell you there's a missing case, false true, in the data. Okay, just to mention, you can match on strings. Okay, you have some input, which is a string here, and you match on the string Robert or William, and hello, it gives a short name here, hello Bob, hello Bill. Otherwise, you keep the original name. So this name here can match on a string here. Okay, one thing to watch out for is if you define a value here, Bill Long is called William, and you put that here, this will actually be a variable, Bill Long. It'll match that value, and this last rule will never be matched. It doesn't matter that this name is in scope here, but you can, if you want, mark things as literals. Okay, you usually use uppercase for those. So Bill Long is William, Bob Long is Robert, and you can use those then, and those are effectively the literal string William and the literal string Robert. Okay. Okay. So let's take a look at using guards here. We saw one of these before. You can use when guards. It's a little, there's a high-low game that people like playing. Guess the secret number, higher, lower, so on. Yeah, you got it. And we have let the guess is read from the line, and when we have a guess, then if the guess is greater than a secret number, do something. When the guess is less than a secret number, do something, and otherwise fall through to the bottom case. Okay, they're the guards. Okay, just to say we can match on structured data like lists, for example. So you can match on a list of 0, 1, 2, or 3, and then we work out the lengths here. Just as an example, not a particularly realistic code, but just showing the examples of matching on the elements of a list here. Okay, just to say that patterns occur all over the place in F# code. You can have patterns here, and when you define functions, the input is matched against a pattern, and the inputs of a function here can be matched against the function in this position here. We have the patterns that occur in match expressions here. And we also have when we have exception handling, we try with this pattern or that pattern. We match the exception that gets caught against the various patterns here. And just to say, you can also use patterns in these positions for each x, y in the expression and so on. Right, so that's enough on pattern matching. There's a few other topics in pattern matching that we didn't consider in that part of the talk. There's how to pattern match against .NET objects and how to use something called active patterns. Those are covered in the F# books that we talked about at the end of the last tutorial, and we'll show again at the end of this one. So we'll look at a little bit of object-oriented programming now. And object-oriented programming in F# is very, very sweet. And here's a typical bit of object-oriented programming, the sort of the general pattern that you'll see for objects in F#. You define a type, an object, we give it a name here, some object type, and it'll take arguments. And you're implicitly defining a constructor. You have some internal values, some internal state if you're using imperative programming, and some members, some properties, and some methods here. And you can make new objects, and you can also have interface types down here. Okay, so let's have a look how that looks in practice. We have an object type here, vector, with inputs dx and dy here. Now this is implicitly defining a constructor here. So you have a constructor here that you give a dx and a dy. And then you publish those results, those inputs. So we're publishing two inputs, dx and dy, as properties. We have another property called length, which computes the square root of dx squared and dy squared to give the length of the vector. Then we scale that vector by a particular constant, bringing a new vector, calling back to the constructor each time we scale the vector. Okay. So you have inputs to the object construction, exported properties, and an exported method called scale. Okay, we can define some internal state to the object. So this is a pre-computed value, norm2, which can then be used throughout the object, internal pre-computed values and functions. Okay, just to say, the fact that you can have any functional programming code, your let bindings, your values and your function definitions here, in this section here leads to a very nice smoothness in transition between sequential programming, between scripting programming and more structured object-oriented programming. So for instance, you have some very nice, there's a great example by Luke Hoban on his blog. Luke Hoban works on the F# team here at Microsoft. And he has this lovely 50 lines of functional code implementing Huffman encoding. And then he shows how to turn that into a .NET object that can be accessed from any other .NET language in a very reliable way. So he indents it by 4 spaces. He puts his type Huffman encoding here at the top, taking the input, the frequency table, which is a key input to this code. And then he publishes, there's 2 functions defined in this code called encode and decode, and he publishes those. By default, all of this code is private, and the ones that are labeled members are public. So this is the API. You now encode the function, you have the input, you encode it, and you decode, and you have an object for use. And now, because you're using sequences as your inputs here, and sequences as your input here, this will be immediately usable from any other .NET language. It's got a form that's very recognizable and usable from C# and Visual Basic, for example. Immutable inputs, internal tables, and publish access to those. Just to say, you can do imperative programming with objects if you want. Okay, so this is actually objects plus imperative programming, we have some internal state here, and we label that state as mutable, that it can be changed. And we can publish that internal state as the dx and dy values here. And we can have a function move, which actually modifies the dx and the dy contents of the object. Okay. Okay. So we'll take a look at some OO design patterns in F# very, very quickly. We saw one of these at the start of at the start of the tutorial series in the very first part of the tutorial. Okay. Okay, so let's take a look at the command pattern here. And this might be an example where we actually had a simulation engine. And now, so let's take a look at the elements here. First, we've got a type of vectors here, modeling three-dimensional vector. And we have a type of degrees here, because we're going to annotate our floating number with a unit of measure called degrees. Okay, so we're going to define the model of a Mars rover in a simulation. And it's a simulation. We're going to have some mutable simulation state. One of the aims of F# is not to necessarily make all your programming pure. There are various ways to represent simulation state. Of all the sins of imperative programming, representing simulation state using mutable state is absolutely okay. It's really not a problem. You want to use imperative programming. Some of the key places you're going to use it is in your simulation state, your core infrastructure, your core representations of your of the state of an algorithm, of a simulation, or in your display state as well, is also the actual state that captures the scene graph, for example, of that you might be displaying, or no, the actual objects that represent the displayed scene graph. That is okay. In this case, we're using simulation state, and if you're doing a simple simulator, that's a reasonable thing to do. There are other more functional ways of representing that simulation state. There are advantages to using the functional ways, but we won't be going through those. It's a more advanced topic about when to choose to use a functional style here. So we have the direction and the velocity of the rover. It starts off going forward, and the velocity here is not moving, 0 in each direction. And we publish those as direction and velocity. And we also indicate whether it's, you might have other members which, for instance, crashed into a rock, and actually it's always being set into false, but you might also have an additional piece of state saying crashed. Okay, that might start off being false here, and then you would return crashed here as your, and maybe you might also saying crashed into might be nothing to start with, none, and crashed into equals some rock, for example. Might be an indicator that it crashed into a rock. Okay, but we'll go back to the original code where we just say it has never crashed into a rock. And the rest of your object might have a design where you can rotate the direction. So of course this would be, you set the direction to be direction plus the change here. Okay. And just to say, you actually wouldn't need this type annotation here. When we look at the types here, we'll see that it's pretty straightforward that the change here has to be a floating point number, which is in degrees. And of course, the F# type inference system works that out, that this change is a floating point number in degrees. Right, so similarly, you might have acceleration, such as your velocity here. You would scale the velocity vector depending if it's, no, you would add the velocity vector to you'd add a portion to the velocity vector. In fact, we might just change the design to be like speed here, which would be an initial 0.0. Okay, and then speed, we'll get speed plus x. Okay, great. And this would change to speed, and the velocity vector here would change to speed. Great. Right. So now the command pattern is the one we looked at in the first, where we're modeling in the first tutorial, where we're modeling commands as actions, functions, which will take a Mars rover and modify the rover. And a typical pattern of this is you add commands into a queue. So you have various rover commands, and you keep that would place it in a data structure, and those are processed through a discrete event simulation. So now we have various commands, such as the accelerate command, the brake command, turn left command, and those are simply building commands which take the rover and do an appropriate action. Okay. And in the sample code, you'll just see some additional samples of perhaps writing a program to move that moves the rover in a particular way. So while the rover isn't crashed into a rock, we compute the destination to the direction, and if it's to the left, we turn left, and if it's to the right, we turn right, and so on, straight on. Okay. Right. So as a sample exercise in object-oriented programming, we'll leave this. we'll look at the solution to this sample straight away. So the aim is to do a line analysis on a file, which takes a path to the file, reads the file, and then computes the line count, unique lines, average line frequency, and the average line length. So let's take a look at this exercise solution. Okay. Right, so here's our line analysis here. We're going to use some imperative programming here to help do the line analysis. So we're going to build an object which represents the analysis of this file. Okay, so you'll see this nice mix of object-oriented programming with functional data analysis here. So we have a file path here, and then we do some computation which summarizes here. It's actually an imperative computation, but the summary in the end is used in an immutable way, this dictionary that we have, and it's contained within this object. So we compute these line counts. So we have a dictionary here. We create a .NET dictionary, and we use a file. This is the same as using in C#. We use a file to create a stream reader for the file path. Let's be able to read off the lines. While we're not at the end of the file, we read from the line. If the dictionary doesn't contain the line, we enter the value 1. And if it does, we increment the current count in the dictionary by 1. Okay. And then, so we've got our summary, which is the dictionary. And now we're going to return the number of times a particular line occurs in the file. So we're going to take a line, going to take the line count, and if the line count contains the key, then it returns the number of times here that it occurs. Otherwise, we return 0. The number of unique lines in the file, we take the keys from the line counts and we sort those. And we take the keys here, and we have the unique lines, not the number of unique lines, it's actually returned the unique lines here in the file, sorted. Okay, now we want the average line lengths. We can take the line counts, and because it's a dictionary, we can look at it as a sequence of key value pairs. So we can map over that. We match with the pattern key value for matching key value pairs. We get the key and the value out of the dictionary. Then we get the length of each line and the number of times it occurs. And then we convert that to a floating point number, and then we take the average of those floating point numbers. So, and the last one, we can turn the average number of times each line occurs. We can take the line counts and we average by the number of times each line occurs, which is the value in the dictionary, in the key value pair, and we have the overall line frequency. Okay, so let's define this type now in our F# interactive. And we'll do the analysis of a particular file, say the WinINI file, and we'll find that all the unique lines that occur in the file here. So I should be able to, okay, and we now find the average line length in the file is 12.9, and the average line frequency in the file is 1.0. Okay, so each occurs exactly one time. Okay. Okay, as part of what we've just seen, we've seen some simple imperative programming in F#. Just a recap of what we're doing here. You can do imperative programming. You can say let mutable x equal 1 and so on. Okay. Some data structures are inherently mutable. So we have a reference cell, it's called a ref actually in F#, which has the contents of some type, and you can create new ones of those, and you can create a reference cell and you can set the values in the reference cell. Take the contents of the reference cell and add 1, for example. Now there are other very important mutable collections, resize arrays, dictionaries, hash sets, and arrays. But a very common use of these mutable .NET collections is that you will make one of these and you'll hide it inside an object and you won't expose it. It'll be an isolated use of a mutable data structure, and then after it's created, it won't be changed anymore. That's a very common coding technique, just like the one we did with the with the line analysis type here. From the outside, once a line analysis has been constructed, it is an immutable object. It cannot be changed and can be passed to any part of your application safely. So, okay, great. So, that's actually all we have in the tutorial today. So thank you very much for having me here on Channel 9. Just to wrap up with some general information about learning F#, we've covered really the basics of F# programming, pattern matching, working with data, some basic imperative programming, using .NET libraries. And I'd encourage you to just go and play and learn F# by using F# Interactive in Visual Studio and just run yourself through some of the tutorial samples we've had today or through some of the other great tutorial material on the web. If you're looking for samples, you can get samples on MSDN. There's another great way to work is just take some existing F# code base and use GoToDefinition and work your way through how they've written up their F# code. A lot of people who are familiar with .NET like to get the tool, the Reflector tool, and just run it over some generated, the assembly that gets generated by some F# code, and have a look, how does this stuff actually get compiled? If I look at the compiled form as if it was C# code, how does it actually work underneath? And that can be very informative for understanding how F# works. There's also a great article coming out about F# on the Common Language Runtime. You can get a feeling for how does F# map down there and what does the Common Language Runtime have special that's in it for running languages like F#, for instance, tail call support. If you're looking for forums on F#, there are these HubFS forums is the common meeting place for a lot of the F# community, a great place to ask questions. Stack Overflow is also a wonderful place, wonderful resource for asking questions and for looking at the answers for frequently asked questions from other F# users. Just to say there are some Codeplex projects, and we'll talk about the books. And another great way to learn functional programming is just to go and learn OCaml or Haskell or Erlang or some of the other functional programming languages. They're also syntactically slight variations on slightly different to F#. F#, of course, is also a great first place to learn functional programming. Okay, so we're going to wrap up there. Right, latest books about F#. We have the ones we've been talking about, functional programming in F# with examples in F# and C#. We have Programming F#, the O'Reilly book. Beginning F# is a great book as well. More domain specific is F# for Scientists, and we're just working on the second edition of Expert F#, which will probably be out by the time you're watching this video. And just a taster for the advanced tutorials, we'll be looking at async and parallel and reactive programming in the advanced tutorials, along with a couple of other more advanced topics. But thank you very much, Charles, for having me here on Channel 9.
Thank you for coming.
Pleasure.